At 3:10 on a June morning in 1941, a Vickers Wellington MK-IC touched down on a rain-slick dispersal at a Royal Air Force station somewhere in Norfolk. The pilot eased back the throttles, felt the tailwheel kiss concrete, and brought 11 tons of fabric-covered bomber to a stop as ground crew jogged out through the mist with chalk and clipboards. The engines ticked as they cooled. A wireless operator climbed down through the belly hatch, boots squelching in puddles that reflected the dim perimeter lights. Nobody spoke much. They had been airborne for 7 hours, most of it over the North Sea and the Frisian coast, and the adrenaline was draining away into the cold dawn air. The chief ground engineer walked a slow circle around the fuselage, marking each hole with a stub of chalk, small caliber, probably from a night fighter's machine guns. Larger tiers where 20mm cannon shells had punched through and kept going. He counted aloud, making neat tally marks on a scrap of paper clipped to his board. 50 holes, 100, 150. At 200, he stopped, looked up at the captain still strapped in the cockpit, and said in a voice flat with fatigue and a kind of disbelief, 200, sir. Then he held up the chalk. Just a nub. He had run out. The airframe was still straight. The wings held their dihedral. The bomb bay doors had closed and locked. The fabric skin, a sandwich of Irish linen doped with cellulose acetate and aluminum powder, hung in tatters over sections of the fuselage, flapping gently in the morning breeze. Underneath, a lattice of light alloy strips crisscrossed in a diamond weave, each member no thicker than a man's thumb. It looked fragile. It looked like something you could kick apart with a good boot. German technical officers had thought exactly that. Months earlier, near Wilhelmshaven, they stood around a downed Wellington in a muddy field. One officer walked the perimeter, counting holes. Another took photographs. A third kicked the fuselage, expecting the lattice to buckle. It flexed. It did not break. He kicked again. Harder. The structure absorbed the blow and returned to shape. He stopped kicking. In the assessment report filed later that week, the summary line read, fabric construction, primitive methodology, expected catastrophic structural failure. Then, in a margin note added by hand, stopped counting at 200 perforations. Airframe integrity inexplicably maintained. The word inexplicably was underlined twice. Why? Why did a bomber covered in doped linen, a material that belonged on biplanes from the previous war, become the aircraft that Luftwaffe intelligence learned to fear not for its speed or its bomb load, but for its refusal to come apart? Why did this design, which looked outdated beside the sleek metal skins of the Heinkel 111 or the Junkers 88, survive more punishment per sortie than aircraft built from riveted aluminum panels? The answer is a lattice. The answer is one engineer's obsession with airships. The answer is night bombing doctrine born from daylight massacre, and coastal patrols over black water where a searchlight could turn the Bay of Biscay into a killing floor for submarines. The answer is damage tolerance as a philosophy, and maintenance crews who could patch 100 holes before breakfast and send the bomber back into the stream by nightfall. By mid-1941, hundreds of Wellingtons were operational. Each carried 5 or 6 men, pilot, navigator, bomb aimer, wireless operator, gunners. Each cruised at 200 to 235 miles per hour, roughly 320 to 378 kilometers per hour. Service ceiling reached 18 to 20,000 feet, about 5.5 to 6 kilometers, depending on the mark. Combat radius stretched from 1,000 to over 2,000 miles, 1,600 to 3,200 kilometers, depending on fuel and bombs. And between 1938 and 1945, Britain built 11,461 of them. 11,000 fabric bombers that the enemy kept shooting full of holes, and that kept flying anyway. The internal bomb bay could swallow up to 4,500 pounds of ordnance in the early marks, about 2,040 kilograms. Though coastal variants often carried mixed loads, bombs, depth charges, flares, tailored for hunting submarines in the approaches west of France. Picture the moment in layers. Clothes on the pilot's gloved hand inside the cockpit, fingertips brushing the geodetic longeron. The intersecting metal strips forming a lattice you could see through to the fabric skin beyond. Pull back to the operations room at Bomber Command, where pins on a map trace the night's routes over the Ruhr and Hamburg. Each pin representing one aircraft and 6 lives betting that distributed loads would bring them home, even when those loads included shrapnel. Then drop back to the dispersal at dawn, where a fitter's palm slaps a fresh patch of doped linen over a fist-sized tier, the acetone smell cutting through the damp Norfolk air, micro to macro to micro. The Wellington story lives at both scales. Here is the key insight. The thing that makes the 200-hole anecdote more than barracks mythology, geodetic construction divides stress into a mesh. When you lose one node in the mesh, the load finds another path. Strip 41 tears through. Strips 39 and 62 take up the slack. It is not invincible. It is redundant. And redundancy, coupled with disciplined maintenance and an operational tempo that prioritized rapid turnaround over perfect repair, created structural endurance that the enemy could damage extensively but not easily kill. The fabric was a liability in some ways. It burned when incendiaries hit. It tore easily. It required constant care. But the frame underneath was a different kind of wager, one that paid off in the long nights over the Ruhr and the cold patrols over the Atlantic, where coming home with holes mattered more than coming home without them. This is the story of Barnes Wallis and a lattice borrowed from airships, of Heligoland Bight, where daylight doctrine died in fire, of the pivot to darkness and the sea, of radar and searchlights that could find a submarine on the surface at midnight, of sorties measured not in perfect machines but in available machines, and of a campaign that ran on the arithmetic of repair speed and return rate. The German inspectors stopped counting at 200 holes. The Wellington did not stop flying. That difference is where the story begins. The lattice begins with an airship that never fought a war. In 1929, Barnes Wallis was chief designer at Vickers, working on the R100, a British rigid airship intended to prove that lighter-than-air travel across the Empire was not just feasible but elegant. The R100 needed to be light. It needed to be strong, and it needed to distribute loads across a framework that could flex in wind shear without tearing itself apart. Wallis solved the problem with geodetics, a term borrowed from geodesy, the science of measuring the Earth's curved surface. He built the airship's frame from a lattice of intersecting diagonal members, each one sharing stress with its neighbors in a continuous mesh. When one member bent, the load redistributed. When wind gusted, the structure breathed. The R100 flew to Canada and back in 1930 without structural failure. The competing government design, the R101, built with a conventional longitudinal frame approach, crashed in France on its maiden voyage to India, killing 48 people. The wreckage burned for hours in a French field near Beauvais. Investigators found the longitudinal girders twisted like pretzels. The frame collapsed in on itself. The R100's geodetic lattice had flexed in worse wind shear over the Atlantic and returned home straight. The geodetic principle had won the argument in the cruelest possible way. Wallis kept a photograph of the R100's lattice frame on his desk at Vickers for the rest of his career. He was obsessed with redundancy, with structures that refused single points of failure. He did not waste the lesson. By the mid-1930s, he was convinced that the same lattice logic could be applied to an aircraft fuselage. Bombers of the era, Handley Page Hayfords, Vickers Virginias, used heavy spars and stringers with fabric or metal skin, doing much of the load-bearing work. Wallis proposed the opposite. Make the internal skeleton do everything, and let the skin simply keep the wind out. The Air Ministry issued Specification B 932 in 1932, calling for a twin-engine medium bomber with a range of over 1,000 miles and a bomb load of 1,000 pounds minimum. Vickers submitted a design they called the Type 271. The Air Ministry looked at the blueprints, saw a fuselage made of woven metal strips covered in fabric, and hesitated. It looked experimental. It looked risky, but the performance numbers were compelling. And in 1936, Vickers received a contract for a prototype. They called it the Wellington. The structure was built from light alloy, primarily aluminum, with small amounts of copper, magnesium, and manganese, formed into strips roughly 1 inch wide and 1/16 of an inch thick. These strips, called lozenges in the shop, were riveted together at their intersections to form a continuous basket. Weave running the length of the fuselage and around the circumference of the wings. Each intersection point was a node, each node connected to 4 or more neighbors. The lattice had no primary load path because every path was primary. You could not cut a single member and expect catastrophic failure because the load simply flowed around the gap, like water finding a new channel. Over this skeleton, workers stretched fabric, Irish linen, tightly woven, treated with multiple coats of cellulose dope mixed with aluminum powder to tighten the weave, seal the pores, and provide a smooth surface for airflow. The dope smelled like acetone and dried to a hard, brittle finish that cracked if you bent it too sharply but held its shape under normal aerodynamic pressures. The fabric added almost no structural strength. It was there to create a surface. To keep the rain out and the airflow laminar, all the real work happened in the lattice underneath. The result was an aircraft that looked delicate and performed like a workhorse. The first prototype flew on June 15, 1936. From Brooklands, test pilots reported handling that was stable if somewhat heavy on the controls, and an airframe that did not creak or flex the way fabric-covered biplanes often did. The geodetic frame was stiff in torsion, meaning the fuselage did not twist along its length under load, which translated to better control response and less fatigue, cracking around attachment points. By 1938, the Wellington MK. I was entering service with RAF Bomber Command. It carried a crew of 5, later 6 when a second gunner was added. The power plant was twin Bristol Pegasus radial engines, each producing around 1,050 horsepower, roughly 783 kilowatts per engine. Maximum speed was about 235 miles per hour at 15,000 feet, approximately 378 kilometers per hour at 4.6 kilometers altitude. Cruising speed was closer to 200 miles per hour. Service ceiling on paper reached 18,000 feet, though operational missions rarely exceeded 15,000, except in extremis. The bomb bay was internal, a long tunnel running nearly the full length of the fuselage beneath the wing, carry-through structure. Early marks could carry 4,500 pounds of bombs, roughly 2,040 kilograms, typically in the form of 18 250-pound general-purpose bombs, or a smaller number of heavier weapons. The bay doors were clamshell style. Hinged along the bottom edges of the fuselage, they opened by rotating inward and upward, clearing the way for bomb release without the doors extending into the slipstream. This was important. In aircraft with stressed skin construction, battle damage that bent a fuselage frame could jam the bomb bay mechanism, forcing crews to either jettison the load manually or return home with live ordnance. The Wellington's lattice, because it distributed loads and resisted localized buckling, rarely suffered that failure mode. The bay opened and closed even when the surrounding structure was ventilated with shrapnel holes. By late 1939, Wellington production was ramping up. Shadow factories at Chester, Blackpool, Squires Gate, peak output, 70 aircraft per month. Each fuselage took hundreds of man-hours to build, every strip cut, formed, reveated by hand. But once built, it took only a dozen hours to patch. That asymmetry would prove decisive. The Air Ministry and RAF leadership saw the Wellington as a modern medium bomber, suitable for daylight operations in formation with fighter escort. Following the doctrines of the time, heavy defensive armament, a powered nose turret with 2 machine guns, a tail turret with 4 or later 2 machine guns, and beam positions for additional gunners, was supposed to make massed bomber formations difficult to intercept. Mutual defensive fire would create overlapping fields that no fighter could penetrate without taking lethal damage. That was the theory. It assumed fighters would attack from astern in leisurely stern chases. It assumed visibility would allow gunners to track and engage at range. It assumed the bombers could maintain tight formation under fire. Reality had other ideas, and those ideas arrived with tracer fire over the Heligoland Bight in December 1939. December 18th, 1939. 24 Vickers Wellingtons from Nye, 37 and 149 squadrons climbed out from their bases in East Anglia just after dawn, formed up over the North Sea, and turned east toward the German naval base at Wilhelmshaven. The mission brief was straightforward. Attack German warships in the Schillig Roads anchorage in broad daylight, relying on tight formation and mutual defensive fire to survive the return journey. The weather was clear. Visibility was excellent. The bombers flew in neat Vicks of 3 wingtip to wingtip, their gunners scanning the sky for Messerschmitt fighters that intelligence predicted would be occupied elsewhere. The doctrine was simple, and it was wrong in ways that would become apparent within the hour. The German early warning radar along the coast picked up the formation while it was still over international waters. Luftwaffe fighters scrambled from Jiva and Wangerooge. Messerschmitt Bf-109s and Bf-110 twin-engine heavy fighters climbed hard, guided by ground controllers who fed them intercept vectors in real time. The Wellingtons pressed on. Some crews saw the fighters climbing through broken clouds below. Others did not see them until the first bursts of cannon fire tore through the formations. The attacks came from ahead and below, not from astern where the Wellingtons' tail guns had fields of fire. The German pilots had learned quickly that attacking from behind gave the bomber gunners clear shots and allowed the formation's overlapping fire to concentrate. So they came in fast from 11 o'clock low and 1 o'clock low, climbing into firing position, releasing 2-second bursts of 20mm cannon and machine gun fire, then breaking away beneath the bombers before the turrets could track them. The Wellington's nose turrets, mounting 2 rifle-caliber machine guns, could not depress far enough to engage. The beam gunners, firing through open hatches, found the slipstream tearing their aim apart. The tail gunners fired at empty sky where the fighters had been seconds before. 5 Wellingtons went down over the target area. 2 more fell on the way home. Others returned with engines shot out, control surfaces damaged, hydraulic lines severed. 1 aircraft, flown by a pilot named Guy Gibson, who would later become famous for leading the Dambusters raid, landed with fabric hanging in strips from the fuselage, and 1 engine fire blackened and seized. The geodetic lattice underneath was intact. The aircraft had flown home on asymmetric power with half the skin missing. But 7 aircraft and 42 men were gone, a loss rate approaching 30% for a single mission. Bomber Command grounded the Wellington force for daylight operations within a week. The post-mission analysis identified 3 critical vulnerabilities. First, the fabric skin. For all the geodetic frame's structural resilience was catastrophically flammable. German fighters had begun loading a mixture of armor-piercing and incendiary ammunition, typically 1 incendiary round for every 3 or 4 armor-piercing rounds in the belt. When an incendiary round punched through the fabric and ignited the doped linen, the fire spread rapidly along the airflow, consuming the cellulose and aluminum powder in bright white flames that could not be extinguished from inside the aircraft. The lattice did not burn. Aluminum alloy melts at around 1200 degrees Fahrenheit, 650 degrees Celsius, far above the temperature of burning fabric. But the loss of skin destroyed the aerodynamic envelope, and several aircraft were seen to enter uncontrollable spins as airflow separated chaotically over the exposed frame. Second, the fuel tanks in the wings were not self-sealing. Early war RAF doctrine had not prioritized fuel tank protection. Assuming that fighter escort and formation discipline would prevent sustained attacks, a single armor-piercing round through a tank could drain hundreds of gallons of fuel in minutes. A tracer or incendiary round could ignite the fuel vapor in the tank's ullage space, the gap between the liquid fuel and the tank's upper surface, turning the wing into a bomb. Several Wellingtons were seen to explode in mid-air when fire reached the fuel system. Crews had no time to bail out. They simply ceased to exist in a bright orange flash visible from 20 miles away. Third, armor protection for the crew was minimal. The early Wellington Marks had no armored bulkheads behind the pilot's seat, no armor plate around the fuel tanks, and no armored glass in the cockpit canopy. A single burst from a Bf-109's nose-mounted cannon could kill or incapacitate the pilot and co-pilot, leaving the aircraft to fly itself into the sea or spiral into the ground with the rest of the crew, still alive and helpless in the back. The geodetic frame could survive the damage. The men inside often could not. German propaganda made much of the December 18th raid. Newsreels showed wreckage being hauled from the shallow waters off Wilhelmshaven. A Luftwaffe technical officer appeared on camera, gesturing at a crumpled Wellington fuselage, dismissing it as fabric construction. Primitive, easily destroyed. The commentary noted that British bombers were covered in cloth, like circus tents, implying a kind of technological backwardness that German engineering had surpassed. The footage was intended to demoralize British public opinion and reassure the German population that the Reich's air defenses were impenetrable. In a narrow sense, the propaganda was correct. Fabric bombers flying in daylight against modern fighters and radar-directed interception were flying coffins, but the propaganda missed the structure underneath the fabric, and it missed what would happen when the British changed the equation by taking the bombers into the dark. Bomber Command's response was immediate and multifaceted. First, daylight bombing operations over heavily defended targets were suspended indefinitely for medium bombers. The Wellington force would transition to night operations, where German radar was less effective, where fighters had difficulty with interception geometry, and where the bomber's camouflage and lack of running lights made visual acquisition nearly impossible. Second, a crash program began to retrofit self-sealing fuel tanks across the Wellington fleet. The self-sealing technology used layers of rubber compounds that swelled when exposed to fuel, plugging bullet holes automatically. The tanks added several hundred pounds to the aircraft's empty weight and reduced fuel capacity slightly, but they reduced catastrophic fuel fires by an order of magnitude. Third, armor plate was added behind the pilot's position and around critical systems. Again, weight increased. An armored seatback weighed around 75 pounds, roughly 34 kilograms, but survivability climbed. Fourth, the fabric was treated with fire-retardant compounds in addition to the standard dope, slowing the spread of fire long enough for crews to attempt extinguishing measures or, failing that, to bail out. By mid-1940, the modified Wellingtons were returning from night raids over the Ruhr and Rhineland with battle damage that would have destroyed them 6 months earlier. Incendiary strikes burned through the fabric, but self-extinguished when they ran out of untreated material to consume. Fuel leaks slowed to trickles as the self-sealing tanks did their work. Armor stopped rounds that would have killed pilots, and the geodetic frame, ventilated with holes from flak and cannon fire, continued to distribute loads and bring the aircraft home. The doctrine had failed. The aircraft, redesigned and redeployed, had not. The lesson was written in the logbooks of squadrons that flew both before and after the changes. In the last quarter of 1939, Wellington loss rates on operations hovered near 10% per sortie for daylight missions over defended targets. By the second quarter of 1940, with night operations and technical modifications in place, loss rates dropped to between 2 and 4% per sortie, depending on the target and the weather. The aircraft was the same geodetic airframe. The tactics and the modifications made the difference. The enemy had stopped laughing. The turning point came not with a single order, but with a slow recognition that darkness was geometry's enemy and the Wellington's ally. By spring 1940, Bomber Command had committed to night operations as doctrine, not desperation. The Wellington force, grounded after Heligoland Bight's bloodshed, re-emerged flying under the cover of darkness over the Ruhr Valley, over Hamburg's docks, over the rail yards at Hamm and Cologne. The losses did not stop. Flak still claimed aircraft. Night fighters still prowled, but the mathematics shifted. German radar could detect formations, but struggled to vector fighters onto individual bombers in three-dimensional darkness. Searchlights could illuminate a target, but the cones of light also told every bomber in the stream exactly where the defenses were concentrated. And the Wellington, its fabric skin now treated with fire retardant and its fuel tanks sealed against leaks, began to return from missions with damage patterns that would have been fatal in daylight. Shredded tail surfaces, punctured wings, fuselages that looked like they had been worked over with an industrial hole punch. The geodetic frame underneath absorbed the abuse, distributed the loads, and held its shape. Then the mission set expanded. In late 1940 and into 1941, Coastal Command began pulling Wellingtons from bomber squadrons and modifying them for maritime patrol. The threat was German U-boats operating in the Atlantic approaches, surfacing at night to recharge batteries and transit at higher speed on diesel engines. British convoys were bleeding tonnage. Merchant ships went down faster than shipyards could replace them. The Admiralty needed aircraft that could patrol long arcs over the western approaches and the Bay of Biscay, detect submarines on the surface, and attack before the boats could crash dive to safety. The Wellington, with its range and payload capacity, fit the requirement. But finding a submarine at night on a black ocean was a problem that bombs alone could not solve. The solution arrived in two parts, both technical, both designed to turn night from cover into killing ground. The first was air-to-surface vessel radar, ASV for short. Initially the Mark II variant, ASV Make II operated in the 1.5 meter wavelength band, roughly 200 megahertz, with a rotating antenna mounted in blisters on the Wellington's fuselage sides and under the rear of the aircraft. The system could detect a surfaced U-boat at ranges between 3 and 8 nautical miles, approximately 5.5 to 15 kilometers, depending on sea state and the submarine's profile. The radar operator sat at a console in the fuselage, watching a cathode ray tube display that showed returns as bright blips against a dark screen. When a contact appeared, he called range and bearing to the pilot. The pilot turned toward the contact and began a descent. But radar alone had a critical limitation. It could guide the aircraft to within a mile or so of the target, but in the final moments before weapons release. The radar's minimum range, about 1,000 yards, 900 meters, created a blind spot. The crew had to visually acquire the submarine in the last seconds of the attack run, on a moonless night over Blackwater. That was nearly impossible. The second part of the solution was the Leigh Light, named after squadron leader Humphrey de Verde Leigh, who designed it in 1940. The Leigh Light was a retractable searchlight mounted in the Wellington's belly, just aft of the bomb bay. It used a 24-inch diameter parabolic mirror, roughly 60 centimeters, and a filament lamp powered by the aircraft's electrical system, producing a beam with an intensity of approximately 22 million candela at its center. When the light was switched on, it turned a circle of ocean roughly 600 feet across, about 180 meters, into something resembling daylight from 250 feet altitude. 76 meters. The tactical choreography worked like this. ASV radar guided the Wellington to within a mile of the surfaced U-boat. At 1 mile, the pilot began a shallow descent, throttling back to reduce noise. At half a mile, the navigator called out distance to go based on stopwatch timing and airspeed. At a quarter mile, roughly 450 meters, the pilot gave the order, and the wireless operator flipped the switch. The Leigh Light snapped on. The ocean turned white, and if the geometry was correct, a German U-boat appeared in the center of the beam, crew members frozen on the conning tower. Spray from the bow wave lit like silver. The boat itself a long black silhouette against the suddenly visible water. From light on to weapons release. The window was between 10 and 20 seconds. The U-boat's deck gun crew, if they were alert, might get off 1 or 2 wild shots before the Wellington's depth charges or bombs arrived. Most often, they dove for the hatch. The boat's commander would scream for a crash dive, but a Type 7 U-boat needed 30 to 40 seconds to get under enough water to survive a depth charge set to shallow detonation. The Wellington did not need 30 seconds. At 250 feet altitude and 130 miles per hour, roughly 210 kilometers per hour, the typical attack speed, the aircraft closed the final 400 yards in under 7 seconds. The bomb aimer, lying prone in the nose, centered the target in his sight, allowed for drift and the ballistic drop, and released 4 depth charges, each weighing 250 pounds, roughly 113 kilograms. Fell in a stick spaced about 60 feet apart, 18 meters. They were fused to detonate at 25 feet depth, 7.5 meters. When they went off beneath or alongside a surfaced submarine, the water transmitted the shockwave with brutal efficiency. Steel hull plates buckled, welds split, ballast tanks ruptured. If the crew was lucky, the boat stayed afloat long enough for them to abandon ship. If they were not, the boat simply broke apart and sank with all hands. The first confirmed Leigh Light kill came on the night of June 4th, 1942. A Wellington from 172 Squadron, operating out of Chivanor in Devon, detected a U-boat contact on ASV at 0147 hours, 1:47 in the morning, roughly 300 miles west of Brest. The pilot, Squadron leader Jeff Greswell, turned onto an intercept heading and descended. At half a mile, the navigator counted down. At a quarter mile, the light came on. The U-boat, later identified as U-502, was caught fully surfaced, diesels running. Deck crew visible. Greswell held the approach steady. The bomb aimer released 4 depth charges. 2 detonated close alongside the submarine's pressure hull. U-502 went down by the stern in less than 2 minutes. There were no survivors. The engagement, from light on to sinking, lasted 38 seconds. That single kill validated 2 years of doctrine development and technical improvisation. By the end of 1942, Coastal Command had equipped multiple Wellington squadrons with ASV and Leigh Light and the Bay of Biscay, which U-boat commanders had considered a safe transit corridor under cover of darkness, became a hunting ground. German submarines began posting lookouts specifically to watch for the sudden appearance of searchlight beams. Some boats added extra anti-aircraft guns to the conning tower, hoping to shoot down the attacking aircraft before the depth charges hit. It did not change the mathematics. The Wellington had altitude, speed, and the initiative. The U-boat, caught on the surface with engines throttled up and nowhere to hide, had seconds to react. Most did not react in time. And when the Wellingtons took damage from return fire, because the U-boats did learn to shoot back, and 20mm flak could chew through fabric and lattice at close range, the geodetic frame did what it had been designed to do. A Wellington from 179 Squadron returned to base in October 1942 with 63 holes from a U-boat's deck gun stitched across the rear fuselage and tail. The fabric was shredded. 2 lattice members were severed completely. The tail gunner's position was destroyed, the gunner wounded but alive. The pilot flew the aircraft home on trim alone. The control surfaces responding despite the structural damage and landed without incident. The ground crew counted the holes, patched the fabric, and replaced the broken lattice strips The turnaround took 14 hours. The aircraft flew again the next night. Another Wellington from 172 Squadron came back in January 1943 after a patrol that included an engagement with 2 U-boats in succession. The first attack had gone clean. Depth charges dropped. Boat damaged. No return fire. The second attack went badly. The U-boat's flak crew was ready, and they walked a burst of 20mm shells up the Wellington's starboard side, from the tail to the wing root. 8 shells hit. 4 exploded inside the fuselage. 1 severed a control cable. 1 punctured the starboard fuel tank. The self-sealing compound did its work, but not before 50 gallons of fuel had streamed out. 1 blew a hole in the bomb bay large enough to put a man's head through. The geodetic lattice, though perforated in a dozen places, maintained the fuselage's structural integrity. The pilot nursed the aircraft back across 240 miles of open ocean and landed at St. Evil in Cornwall with the airframe bent but unbroken. The maintenance log noted significant battle damage, airframe serviceable for repair. 12 hours later, fitters were stretching new fabric over the patched lattice. This was the turning point. Not a single innovation, but a convergence. Night operations reduced losses. ASV radar gave the Wellington eyes in the dark. The Leigh Light gave it a killing stroke. And the geodetic structure, despised by German propagandists as primitive, gave it the ability to absorb punishment, deliver its payload, and return home even when the mission had gone violent. The enemy had underestimated redundancy, they had underestimated repair speed, and they had underestimated what happens when an airframe is designed not to avoid damage, but to tolerate it. By mid-1943, Wellingtons equipped with ASV and Leigh Light were flying patrol arcs across the Bay of Biscay, every night weather permitted, and the U-boat commanders began filing reports describing the Atlantic transit routes as increasingly hostile. That was bureaucratic language for terror. The darkness that had protected them was now the medium through which a fabric-covered bomber with a searchlight and a radar could find them, illuminate them, and kill them before they understood what was happening. The Wellington had gone from daylight coffin to night predator. The doctrine had turned, the geometry had turned, and the aircraft, with its lattice of aluminum strips and patches of Irish linen, kept turning up over the black water, its light snapping on like a flare over the condemned. The geodetic principle is not complicated. It is simply unfamiliar. Imagine a wire basket, the kind used to carry bottles or hold fruit. Press down on one corner and the entire structure resists, not because any single wire is particularly strong, but because the load spreads instantly through the weave to every other wire in the mesh. Cut one wire and the basket still holds its shape because the remaining wires adjust, taking up the slack. The Wellington's fuselage worked the same way, except the wires were aluminum alloy strips an inch wide and a 1/16 of an inch thick, and the weave formed a continuous helix spiraling around the length of the aircraft. Each strip ran at an angle, crossing its neighbors to form diamond-shaped openings roughly 6 inches across at their widest point, where 2 strips crossed. A revet pinned them together, creating a node. A typical Wellington fuselage contained over 15,000 of these nodes. When a load applied to any point on the structure, whether from air pressure, control surface deflection, or a 20mm cannon shell punching through, the force distributed through the lattice as tension and compression along multiple paths simultaneously. If one path failed, the load simply rerouted. Strip 41 severed by shrapnel. Strips 39, 40, 42, and 43 absorbed its share of the work. The structure did not weaken catastrophically. It degraded gracefully. This was fundamentally different from the stressed skin construction used in most contemporary aircraft. A Heinkel He-111, for example, built its fuselage from a framework of longerons and formers, longitudinal and circumferential members, respectively, covered with aluminum alloy skin panels riveted to the frame. The skin panels were not decorative. They were structural. They carried bending loads and shear loads in the plane of the skin. When a shell tore through an He-111's fuselage, it did not just make a hole. It created a stress concentration at the edges of the tear, a point where loads piled up because they could no longer distribute through the missing material. Under continued load, aerodynamic pressure, control inputs, turbulence, the tear could propagate, ripping along rivet lines or tearing through the skin like fabric. If the tear reached a critical length, the fuselage could buckle or twist, jamming control cables or bending the airframe enough to make the aircraft uncontrollable. More critically, battle damage to a stressed skin aircraft often deformed the underlying frame. A near miss from a flak shell could bend a longeron or twist a former without penetrating the skin at all. The deformation might be invisible from outside, but inside, It could misalign components, bind control runs, or jam the bomb bay doors. Repair required cutting away the damaged skin panels, straightening or replacing the bent structural members, and then fabricating new skin panels to fit. The process took days, sometimes weeks, depending on the extent of the damage and the availability of parts. A damaged He-111 or Junkers Ju-88 often sat in a hangar for a week or more before it could fly again. A damaged Wellington, if the geodetic frame was intact, could be patched with fabric and dope in hours. The other advantage was torsional stiffness. Torsion is twisting along the length of a structure, the kind of force that occurs when one wing generates more lift than the other, or when the tail surfaces deflect asymmetrically in a stressed skin fuselage. Torsional resistance comes primarily from the skin acting as a tube, with the longerons and formers preventing the tube from collapsing. In a geodetic fuselage, the spiraling lattice itself resists torsion, because any attempt to twist the structure forces the diagonal members to either stretch or compress. An aluminum alloy resists both very effectively. The Wellington's fuselage was exceptionally stiff in torsion, which meant that control inputs translated directly to control surface movement without the airframe flexing and soaking up the force. Pilots reported that the aircraft felt solid in maneuvers, even when large sections of the fabric skin were missing. This translated into a doctrine that Bomber Command and Coastal Command began to articulate explicitly by mid-1942, designed for damage tolerance, not damage avoidance. Damage avoidance assumed that, with sufficient speed, altitude, or defensive armament, an aircraft could avoid being hit. The early daylight bombing doctrine had been built on that assumption, and it had failed. Damage tolerance accepted that aircraft would be hit, often repeatedly, and designed systems and structures to continue functioning despite the damage. Self-sealing fuel tanks were damage tolerance, armor plate behind the pilot's seat was damage tolerance, and the geodetic airframe was damage tolerance carried to its logical conclusion, a structure that could lose substantial portions of itself and still bring the crew home. The doctrine extended to maintenance. RAF ground crews developed what became known informally as the chalk and patch system. When a Wellington returned from a mission with battle damage, the crew chief and his fitters would walk the aircraft with chalk, marking every hole, tear, and deformation. Small holes in the fabric, anything under 6 inches in diameter, were patched immediately with pre-cut fabric squares and dope. The dope, applied in multiple coats, dried within an hour. Larger tiers required cutting away the damaged fabric section and stretching new material over the exposed lattice. Then doping it tight. Severed lattice members were replaced by removing the rivets on either side of the break, sliding out the damaged strip, sliding in a new strip, and re-riveting. The entire process for moderate damage, 20 to 30 holes, a few severed strips, took between 12 and 18 hours if the crew worked through the night. By dawn, the aircraft was serviceable again. Compare this to the repair cycle for a stressed skin bomber. A Ju-88 returning with 20 cannon shell hits would require detailed inspection to determine whether any longerons or formers had been bent or fractured. The inspection alone could take hours, often requiring the removal of interior equipment to access the structure. Once the damage was assessed, repairs required cutting away skin panels, straightening or replacing structural members using jigs to ensure alignment, fabricating replacement panels from sheet stock, drilling rivet holes, and riveting the new panels in place. Even with skilled fitters and good parts availability, the process typically took 3 to 5 days. If parts were not available, the aircraft sat until they arrived. The Wellington's advantage was not just structural resilience, it was temporal. It could return to the fight faster. This mattered strategically. A squadron of 20 aircraft generating 1 sortie per aircraft per night produces 20 sorties. If battle damage grounds 5 aircraft for a week, the squadron generates 15 sorties per night, a 25% reduction in combat power. If those same 5 aircraft can be patched and returned to service within 24 hours, the squadron maintains its full sortie rate, or close to it, over weeks and months. The cumulative effect was significant. Squadrons equipped with Wellingtons sustained higher operational tempos than squadrons flying comparable aircraft with longer repair cycles. They dropped more bombs, they flew more patrols, they exerted more pressure on the enemy simply because more of their aircraft were available more of the time. Flight crews adapted their procedures to exploit the structure's characteristics. If battle damage severed a control cable, not uncommon with cannon shells tearing through the fuselage, pilots learned to use trim tabs to maintain control, flying the aircraft back to base with throttle and trim alone if necessary. If fabric tore away from a wing section, exposing the geodetic structure underneath, pilots reduced airspeed slightly to keep aerodynamic loads within the diminished capacity of the exposed frame. The aircraft was forgiving of these adaptations because the underlying lattice, even when partially damaged, maintained enough stiffness to keep the flight surfaces aligned and the fuselage straight. There are accounts of Wellington's landing with entire sections of upper fuselage fabric missing, the lattice exposed to the airstream like ribs under torn skin, and the aircraft handling normally enough that the pilot made a standard approach and touchdown. The doctrine was codified in squadron standing orders and training syllabi by 1943. New pilots transitioning to Wellingtons were briefed explicitly on damage tolerance. Expect to take hits. Expect the aircraft to keep flying. Do not panic when you see fabric peeling away or daylight showing through holes in the fuselage. Trust the structure underneath. Ground crews were trained on rapid fabric repair techniques and carried pre-cut patches and dope in maintenance kits deployed to forward airfields. The entire system, aircraft, doctrine, maintenance procedures, was designed around the assumption that combat damage was routine and that the goal was not prevention but rapid recovery. The Germans noticed. Luftwaffe intelligence reports from 1942 and 1943 contain recurring references to the Wellington's ability to absorb damage and remain operational. One report, captured after the war, noted that while individual Wellingtons could be shot down with sufficient firepower, the overall attrition rate required to suppress Wellington operations was substantially higher than for other British bomber types of similar vintage. The report attributed this partly to the geodetic structure and partly to what it described as efficient repair organisation. The German assessment was correct. The British had turned a structural principle into an operational advantage, and that advantage compounded over time. By 1943, the Wellington was being supplemented and eventually replaced in Bomber Command by heavier four-engine types, the Lancaster, the Halifax, which carried larger bomb loads and had longer range. But in Coastal Command, the Wellington remained frontline equipment through 1944, flying anti-submarine patrols over the Atlantic and the Bay of Biscay. The geodetic structure, which had seemed like a risky experiment in 1936, had proven itself not through invincibility but through persistence. It did not prevent damage, it accommodated damage, and in a war of attrition, that was often enough. The Wellington's strategic value was never measured in individual heroics, but in cumulative availability. By early 1943, Bomber Command was transitioning its main striking power to four-engine heavies. The Avro Lancaster could carry 14,000 pounds of bombs, roughly 6,350 kilograms, more than 3 times the Wellington's maximum load, and could reach deeper into Germany with greater accuracy using improved navigation aids. The Handley Page Halifax offered similar capabilities. These aircraft represented the future of the strategic bombing campaign, and as they entered service in larger numbers, Wellington squadrons were progressively re-equipped or transferred to other duties. But the transition took time, and during that time, the critical period from mid-1941 through late 1943, the Wellington held the line. In 1942 alone, Wellingtons flew tens of thousands of sorties over occupied Europe. They dropped mines in the Kiel Canal and the approaches to Hamburg, restricting German naval movements and forcing mine-sweeping operations that diverted resources from other tasks. They bombed industrial targets in the Ruhr Valley, rail marshalling yards, synthetic oil plants, and anything else Bomber Command could identify and reach. The accuracy was poor by later standards, circular error probable often measured in miles, not meters, but the cumulative effect was disruption. Factory shifts were interrupted by air raid alerts. Workers spent nights in shelters instead of sleeping. Rail schedules slipped as crews repaired bomb-damaged track. The damage was rarely decisive on any single night, but it accumulated, and the Wellington's ability to return from missions with battle damage and fly again within hours meant that the pressure never relented. At sea, the impact was more direct. Coastal Command's Wellington squadrons, equipped with ASV radar and Leigh Lights, turned the Bay of Biscay from a safe transit corridor into a killing zone for U-boats. Between mid-1942 and mid-1943, the period historians call the Battle of the Atlantic's turning point. Allied aircraft sank or damaged dozens of U-boats in the Biscay approaches. Not all of those kills were Wellingtons, Sunderlands, Liberators, and other types contributed, but the Wellington's combination of range, sensor capability, and damage tolerance made it a workhorse of the campaign. German U-boat commanders began avoiding surface transits during hours of darkness, which forced them to remain submerged longer, which drained batteries faster, which reduced their operational radius and time on patrol. The strategic effect rippled outward. Fewer submarines on station in the mid-Atlantic meant fewer convoy attacks, which meant more merchant tonnage reaching Britain, which meant the island could continue fighting. The material economics mattered as well. A Wellington's geodetic structure, for all its labor-intensive initial construction, required less strategic material than an equivalent all-metal stressed skin design. Aluminum alloy was a war-critical resource, and Britain's supply was constrained by both production capacity and the vulnerability of supply routes. Fabric and dope, by contrast, were relatively abundant. Irish linen came from domestic sources. Cellulose dope could be manufactured from wood pulp. The ability to repair battle damage with fabric patches rather than formed metal panels meant that maintenance depots required less machine tooling and fewer skilled metal workers. Repair work could be distributed across smaller workshops, even forward airfields with limited facilities. This decentralization made the Wellington force more resilient to disruption. A single bombing raid that destroyed a major aircraft repair depot would cripple a fleet dependent on complex metal panel fabrication. It barely dented a force that could patch holes with linen and brush-on dope. By the time the Wellington began its operational decline in late 1943, it had demonstrated that in industrial warfare, staying in the fight matters more than winning individual engagements. The Lancaster eventually carried the weight of Bomber Command's offensive. The Liberator became the dominant long-range maritime patrol aircraft, but the Wellington had bought time, maintained pressure, and proven that a well-designed structure coupled with disciplined maintenance could sustain a campaign even when the aircraft came home, shot full of holes night after night. The doctrine of damage tolerance, validated by thousands of sorties and hundreds of successful recoveries from what should have been fatal damage, influenced post-war aircraft design and maintenance philosophy across multiple air forces. The geodetic principle itself saw limited application. It was too labor-intensive for mass production in the jet age. But the idea that redundancy and repairability were strategic assets became embedded in military aviation doctrine. The numbers told the story. Loss rates for Wellington night operations in 1942 averaged between 3 and 4% per sortie, depending on the target and the defenses. That was sustainable. Daylight operations in 1939 had seen loss rates approaching 10% or higher. That was not. The difference was doctrine, technology, and a structure that refused to fail catastrophically. Over 2 years of sustained operations, that difference accumulated into thousands of additional sorties flown, tens of thousands of tons of bombs dropped, and dozens of submarines sunk or damaged. The Wellington did not win the war, but it held ground while the tools that would win the war were being built, and it did so by coming home when other aircraft would have gone into the sea. The Lattice outlived the war. Barnes Wallis continued designing after the Wellington, and his obsession with structural efficiency and precision targeting led to the Tallboy and Grand Slam bombs, 12,000 and 22,000 pounds respectively, roughly 5,400 and 10,000 kilograms, designed not for blast effect, but for penetration and shockwave transmission through earth and concrete. The same thinking that had distributed loads across a geodetic frame now concentrated force into a single penetrating weapon. Wallis spent the rest of his career chasing the elegance of physics applied to engineering problems, and the geodetic principle remained a touchstone. Find the loads, distribute them, design for what will happen rather than what you hope will happen. Only a handful of Wellingtons survive. Most were scrapped after the war, their aluminum alloy reclaimed for peacetime industry, their fabric skins burned or discarded. The most complete surviving example sits in the Royal Air Force Museum at Hendon, a Wellington MKIC with sections of fabric removed to expose the geodetic structure underneath. Visitors can stand beside it and see the lattice in 3 dimensions. The spiral of intersecting strips, the nodes where rivets pin the structure together. It is a teaching exhibit as much as a historical artifact. Here is what redundancy looks like. Here is how loads distribute. Here is why 15,000 connection points matter more than any single beam. The doctrine of damage tolerance that the Wellington validated became foundational in post-war military aviation. Modern aircraft design emphasizes fail-safe structures, redundant systems, and maintainability under field conditions, all principles that the Wellington demonstrated operationally. The geodetic structure itself, too labor-intensive for the jet age, faded from use. But the idea behind it, that a system designed to degrade gracefully under damage is more valuable than one designed to avoid damage entirely, persists in everything from airframe design to software architecture. The anecdote about German inspectors stopping their count at 200 holes has become shorthand for structural resilience, repeated in engineering lectures and aviation histories. Whether the exact number was 200 or 250 or varied between incidents, the story endures because it captures a truth about the aircraft. The Wellington absorbed punishment that looked fatal and kept flying. That was not magic. It was math, metallurgy, and a designer who understood that war is a process of attrition, and that the side whose tools break last has an advantage worth building into the structure from the first rivet. The sun is rising over Norfolk again, 1941, or perhaps 1942, or any of 100 mornings when a Wellington came home with more holes than fabric and still rolled to a stop on the dispersal. The pilot cuts the engines, the props tick to a halt, ground crew swarm the aircraft, already marking holes with chalk, already calculating how many patches they will need and whether they have enough dope mixed to finish before the next mission brief. A fitter lays his hand flat against the fuselage where the fabric has been torn away. Underneath, the geodetic lattice is cool to the touch, solid, the aluminum strips still holding their geometry despite the gaps where cannon shells pass through. He presses lightly. The structure does not flex. He nods to the crew chief, already writing in the maintenance log. Serviceable for repair. Estimate 16 hours. Required materials on hand. By dawn tomorrow, this aircraft will be patched, doped, inspected, and back on the flight line. The crew will climb aboard, run the checklist, and take off into another night. The lattice underneath will do what it was designed to do: distribute the loads, absorb the damage, bring them home, again and again, until the war ends or the aircraft does not come back. But tonight, it came back. The pilot signs the logbook. The fitter picks up his brush and dope pot. The Wellington sits silent in the early light, its skin torn, its frame intact, waiting for the hands that will make it whole enough to fight again. The German inspectors stopped counting at 200 holes. They ran out of chalk, or patience, or the willingness to believe that something so primitive could refuse their expectations of failure. They photographed the wreckage, wrote their reports, and concluded that the structure was an anomaly, an outlier, perhaps a fluke of British desperation. The Wellington did not stop flying. It flew through 1941, through 1942, through 1943 and into 1944. It flew over the Ruhr and over Hamburg, over the Black Atlantic and the cold North Sea. It flew with holes in the wings and holes in the fuselage, with engines smoking and fabric streaming behind it like torn flags. It flew because Barnes Wallis had designed a lattice that distributed 15,000 points of connection across an airframe, and because ground crews understood that 12 hours with dope and patches could return an aircraft to war, and because doctrine had shifted from avoiding damage to tolerating it, 11,461 Wellingtons were built. They flew hundreds of thousands of sorties. They came home shot through, burned, bent, and ventilated, and they flew again the next night. The enemy counted holes and stopped at 200. The lattice kept counting nodes, 15,000 of them, each one sharing the load with its neighbors, each one refusing to be the single point of failure. That was the difference. That was the war, not invincibility, but persistence, not perfection, but redundancy, not a single strong member, but a web of connections that held when in one of them failed, the inspectors stopped counting. The Wellington kept flying, and in the arithmetic of attrition, that stubborn refusal to quit was worth more than armor, more than speed, more than any single brilliance of design. It was worth coming home.